Right. Good morning, all. Uh, I welcome you all to the next class, wherein we'll be dealing with to find the reactions and the maximum bending moment, the maximum positive and negative shear force for a simply supported beam subjected to multiple concentrated loads. It will have a series of concentrated loads, okay, using ideal, influence line, ILD, influence line diagrams, right? So directly we'll take on the question. The question is like this: the multiple point loads of 100 kilonewtons, 120 kilonewton, 80 kilonewton, and 150 kilonewton. So there are four loads, okay, with a spacing of 2 meters each. So their spacing in between each of the load is 2 meters each, meaning they will go together like this. These four are always going to move together. Okay, spacing is 2 meters each in between, and these are going to move together. I cannot change their spacing. So this entire sets keep going. If I have a beam like this, so this will keep moving like this, right? And then we have to position these four in such a way that I will have to find the maximum bending moment, okay, negative shear force, positive shear force, right, absolute bending moment, and reactions. So we have to do the placing of all these so that we will be finding the parameters based on the influence line diagrams, using the influence line diagrams. This is the okay. So to start with, I'll first complete the question. This diagram I'll put it up later. Spacing is 2 meters each. Crosses a girder of span 30 meters. So span of the beam is 30 meter from left to right with 100 as the last one. Okay. Then we have to find the reactions, maximum shear, minimum shear, shear force, especially at 10 meters. So find the shear force at 10 meters from left support. Okay, at 10 meters from left support, then absolute maximum bending moment has to be drawn. So this is the question. I'll put up the diagram first. This is your simply supported beam, okay, whose span is 30 meters. Right, I'll call this A, I'll call this B. Then there are these four loads, 1, 2, 3, 4, who are going to move together. The spacing is 2 meters each. Okay, and first load being 100 kilonewton, then this is 120, 80, and 150. This they have told 100 being the leading. Okay, so 100 kilonewton, 120, 80, and 150 is at the last. This is given in the question. Based on this, we have to find the first. Let us find the reactions. Okay, first let us find the reaction. Now I'll just erase this, and if I want to find the reaction, say first RA. So you know now by strength of materials, or we have done so many numericals. When would RA be maximum? When the load is toward, when the loads are towards the A, or when the loads are towards B?
Towards A.
Load towards A. When the loading is more towards A side, the RA reaction value is going to be more. So what we'll do to find the reaction RA, we will place these exactly starting from A in this pattern. Okay, so what are the loads? This is 100, okay, this is 120, this is 80, and this is 150. Correct? Each of them is at 2 meters. So 2, 2, 2, that makes it 6. 30 minus 6 remaining is 24. Right? So this is the positioning of the load to find the reaction RA. Okay, now I know the influence line diagram for this. What is the influence line diagram when I'm drawing for RA, or influence line diagram that is got from unit load? It is going to be in this pattern, right? This being unity, and this is going to be the length of the entire beam, 30. So then I'll have to get the ordinates of the other loads. So I'll call it as Z1, Z2, and Z3, right? And I know the distances. This is 2, 2, 2. Remaining is going to be 26. No, 24. Any doubt with this? We know the standard influence line diagram for reaction at A for unit load. That is a triangular with 1 unit value at this point. So draw that as it is. Placing the load would be, I'll place them with respect to A. Okay, first load is 100, the last load is 150, that will come exactly on A. So you will place the entire set of load. When I remove this and I want to place here, this will go together like this. So 100 will come here when I'm doing for RB. So this is the ILD, and let us get the values of Z1, Z2, Z3, that are the coordinates for getting the value of RA. Okay, now how do I get the Z1, Z2, Z3? So this is Z1. So 1 divided by 30 will be equal to Z1 divided by this distance. What is this? 30 minus 2. Okay, so Z1 divided by 30 minus 2 is going to be 28. So Z1 is going to be 28 by 30. Okay, similarly, 1 divided by 30 is going to be equal to Z2 divided by this distance. This is 30 minus 4. So Z2 divided by 30 minus 4 is going to be 26. So what is the value of Z2? It is 26 divided by 30. Third one, 1 divided by 30 is going to be equal to Z3 divided by this. This value we know, that is 24. 1 divided by 30 is Z3 divided by 24, or Z3 is going to be 24 divided by 30. Please get me these values. 28 by 30 is how much?
0.93.
0.93. Okay. This
0.86.
0.866 and
0.8.
0.8. Okay. So we got the ordinates. Now if I ask you to find the reaction RA, formula will remain same. If there is UDL, it is going to be load into the UDL. It is not a UDL, it is a point load. So when we are getting the reactions for point loads, what is the equation? It is going to be, it is going to be load into the ordinates. Correct? So starting with 150 is the load. Uske niche, what is the ordinate? Is 1. So 150 into 1 plus 80 into Z1 plus 120 into Z2 plus 100 into Z3. Correct? So 150 into 1 plus 80 into Z1 plus 120 into Z2 plus 100 into Z3. Substitute 150 into 1 as it is, plus 80 into Z1 is 0.93, plus 120 into Z2 is 0.866, plus last load is 100 into Z3 is 0.8. Get me this value, please. RA.
408.32.
408.32. Okay, correct. Anybody else, please check. I want one more person to cross verify this, whether you are also getting the same value. I need one more person to cross check.
Same, ma'am.
Same. So what we did to get the reaction at A, we placed all 4 of them together. First load is 100, last load is 150. But the last one will be exactly on point A. That is, they are together. Now if I want to find reaction RB, right? I'll just erase this. Say we want to find reaction RB. So how will we do the placing now? So everything will go towards B, right? So get RB, to get RB, the diagram would be like this. This is A, this is B. Correct? Now they were moving in what order? 100, next was 80, next was 120, then we had 80, and then we had 150. So this same order will go and sit here now. So at B, I will have 100. Okay, from 2 meters, 120, 2 meters, 80, another 2 meters, 150. It's not visible. Okay. Right? So this is how is the placing. So this becomes 2, 2, 2, and this is 24. Right? The ILD for reaction at B, we know for a unit load is going to be like this. This is 1. I need to now get these ordinates. I'll call them as Z1, Z2, Z3, and this is 1. So to find Z1, this is 24 and this is 2, 2 and 2. Correct? Now let us find Z1. To get Z1, it is 1 divided by 30 is equal to Z1 divided by 24. So Z1 is 24 divided by 30 and we have got this value. What is that? 0.8. What
Yes,
is the
ma'am.
value?
Yes, ma'am.
0.8. They are going to be the same values because numbers are same. This is 0.8. Then Z2 ke liye, it is 1 divided by 30 is equal to Z2 divided by this. That is Z2 divided by this distance is 24 plus 2, 26. So Z2 is going to be 26 by 30. I think this is 0.866. Correct? And last one, 1 divided by 30 is equal to Z3 divided by this distance, that is 28. So Z3 is going to be 28 by 30. How much is this value? 0.9 ಏನೋ ಇತ್ತಲ್ಲ 0.92
0.93.
0.93. Yes. So these are our ordinates, not coordinates, ordinates. So once we get the ordinates, RB is going to be the external load that is coming into the ordinates. Right? So loads, let us look at this now. 100 into 1, 120 into Z3, 80 into Z2, 150 into Z1. Correct? So I'll write that 100 kilonewton into 1 because the ordinate at that is 1 plus 120 into Z3 plus 80 into Z2 plus 150 into Z1. Substitute for the values of Z. 100 into 1 plus 120 into Z3 value is 0.93 plus 80 into Z2 value is 0.866 plus 150 into Z1 value is 0.8. How much is RB, please?
Ma'am, 400.88.
0.8.
400.
400.8 kilonewtons. Any doubts with this? Any doubt with this? We have found the values of RA and RB. To get value of RA, we placed all these 4 concentrated loads towards A. And to find RB, we placed them towards B. And we have got their ordinates and we found the reactions. Okay. So this is the procedure to find the reactions RA and RB. Now let us find the shear force. Right. So it's shear force calculations. So I need to first calculate the negative shear force and then I will calculate the maximum shear force. The shear force is to be found at 10 meters from left support. They have asked us to find the shear force at 10 meters from left support. Matlab, this is your AB, okay, who is 30 meters, spanning is 30 meters. And here somewhere I have a point C, which is at 10 meters. And I have to find the shear force at this spot. Yeah. Now, how do we place the loading to get the shear force? So we know the pattern of shear force diagram when we draw the ILD. It is something like this. For all the examples, we have taken the shear force. This is your negative. This is going to be your positive. And then we mark the positives and the negatives ordinates and we multiply. Correct? So the same thing now, but change is where to place the loading. Okay. So placing the train loads, or you can say instead of train loads, concentrated loads is important. So first I will do it for negative shear force. Okay. So when I want to find maximum negative shear force, how I place the loading is I will place the first load exactly at point C and the rest of them continued like this. Okay. So if I draw it neatly, it will look like this. This is your point A. This is your point B. This is the point C, which is at 10 meters, right? The first load, that is 100, will be placed at point C. Okay. 2 meters, after 2 meters, you have a point load of 120. After 2 meters, you have a point load of 80. And after 2 meters, you have a point load of 150. So 10, this is 2, 2, 2, 6. Remaining is what? 4 meters. Remaining distance is 4 meters. So this is the placing when I'm talking of negative shear force. Okay. So negative shear force means the diagram has to be like this. Correct? Because this is how it is, positive and negative. So I'm calculating negative shear force. So obviously I will be looking only for this one. In this now I have to get these ordinates 1, 2, 3 and 4. And these ordinates into the load with the negative sign is going to give me the maximum negative shear force. Okay. So I'll call this as Z1, Z2, Z3 and Z4. Okay. Remember, to get the shear forces, I am placing the first load on point C and then the rest of them following C. Okay. So let us calculate the ordinates. Total 1 divided by 30. 1 divided by 30. And here distances. This is 2, this is 2, this is 2, and this is 4. Okay. And this remaining is 20. We don't need the 20. So 1 divided by 30 is going to be equal to Z1 divided by what? This distance. How much is this? 10. Z1 divided by 10. So what is the value of Z1? It is going to be 10 divided by 30. That is 0.33. Correct? Am I right?
Yes, ma'am.
Right? So then next. 1 divided by 30 is going to be equal to Z2 divided by this now. How much is this? 4, 5, 6, 7, 8. So Z2 divided by 8. Similarly, 1 divided by 30. 1 divided by 30 equal to Z3 divided by 6. And 1 divided by 30 is going to be equal to Z4 divided by 4. Right? Get the values from here. Z2 is going to be 8 by 30. Z3 is going to be 6 by 30 and Z4 is going to be 4 by 30. What are these values, please?
Point
8 divided
0.26.
0.26. Huh?
6.
Okay. Third one,
Point
Z3,
2.
0.2 and Z4,
0.133.
0.13. Okay. Simple. Okay. I placed the 4 loads starting from point C towards the left side. I got the ordinates. Now when I'm writing maximum negative shear force at C, I will multiply the ordinates into the loadings with the negative signs. Okay. So minus 100 into Z1, minus 120 into Z2, minus 80 into Z3, minus 150 into Z4. Okay. So minus 100 into Z1, minus 120 into Z2, minus 80 into Z3, and minus 150 into Z4. You don't want to put minus signs, you get confused. You can write all in plus and at the end you put a negative sign saying it is a negative shear force. That is also fine. But this is always a good practice. So minus 100 into Z1 is 0.33 minus, excuse me, sorry. Minus 120 into Z2 is 0.26. Minus 80 into Z3 is 0.2. Minus 150 into Z4 is 0.133. Get me this value, please.
Minus 63.7.
Minus 63.7. Check ಮಾಡ್ರಿ ಎಲ್ಲರೂ.
minus 60.25.
I have a different value.
minus 100.15.
Minus 100.42.
Yes, 100 point something. Suraj and the one after Suraj who answered minus 60 and something. Please check ಮಾಡ್ರಿ. Minus 100 or 99 point something.
Minus 100.42, ma'am.
minus 100 point.
minus 100.
Yes. So this is your answer for maximum negative shear force. Now tell me how you will do for maximum positive shear force. If I ask you to do for maximum positive shear force, so load placing will change now. Okay, then your positive figure will come into picture. So load placing would be, this is your beam of 30 meters and this is the point C where I have to calculate the maximum and negative and positive shear force. When I was doing negative, I placed the first load here and the train followed like this. Now when I'm doing for positive shear force, the last load comes over here followed by the other loads. Okay, keep this in mind. Here the last load is coming now. So first load was how much as 100 kilonewton. This was 120. This is 80, and this was 150. Correct. So 2 meters each there. This is 10 meters because we know C point is at 10 meters. These are 2 meters each. So 20 May. This is 2, 4, 6. What is the remainder? 20 minus 6 is 14. So the placing of the loads is important for positive shear force. For positive shear force, your last load will come on C. For negative shear force, your first load will come on C. Okay. Now this is easy. Now how do we go ahead with the positive values to get the ordinates? I will take the positive diagram. This is 1. This is 30. Correct. Get these ordinates. 2, 3, 4. I'll call it as Z1, Z2, Z3, Z4. Z1 is at 10 meters. This is 2, 2, 2, and 14 meters. Right? Let us calculate the ordinates. 1 divided by 30 is equal to Z1 divided by this total distance. How much is this? Total is going to be 20. Z1 divided by 20, or Z1 is 20 by 30. Next, 1 divided by 30 is equal to Z2 divided by this distance. That is 14 plus 4, 18. So Z2 is going to be 18 by 30. Third one, 1 divided by 30 is equal to Z3 divided by this. 14 plus 2 is 16. Z3 divided by 16. Okay, so Z3 value is going to be 16 divided by 30. And last one, 1 divided by 30 is equal to Z4 divided by 14. Right? So Z4 is going to be 14 divided by 30. Get me these values, please.
0.66.
0.66,
0.6. Z2 0.6.
0.6,
0.533.
0.53, and
0.466.
466. Thanks, Pragati. Okay, so you find the ordinates. And then if I want to find the maximum positive shear force at C. Okay, so at C, when I'm calculating, it is going to be 150 into Z1 plus 80 into Z2 plus 120 into Z3 plus 100 into Z4. Right? So 150 into Z1 plus 80 into Z2 plus 120 into Z3 plus 100 into Z4. Substitute 150 into Z1 is 0.66 plus 80 into 0.6 plus 120 into 0.53 plus, what is the last loop? 100 into 0.46. Okay, get me this value, please.
257.56.
Correct. 257 point something. Right? So this is positive shear force value. Okay, kilonewtons. Positive shear force value. So for positive, I will put the last force at C. For negative, I will put the first force at C. Clear? So these are the shear force calculations. Now we have to go for the bending moment calculations. So there is a little change in the bending moment here. bending moment calculations. Okay, so for bending moment calculations. Now, when I'm taking the bending moment calculation, I will be taking the average of the loads. Okay, average of the loads means what? This is our beam. I have a point C given to us, which is at 10 meters. Remaining distance is 20 meters. This is C, this is A, this is B. And we have 4 loads. 1, 2, 3, 4. Starting with 100, 120, 80 and 150. Now we have to put up a table and we have to get the average load. Average means what? Average load between or in the portion AC and in the portion BC. When the value of AC and BC, whenever whichever is higher, for that sector of that pattern, we will get the maximum bending moment. Okay, so what I said I will show. I mean, if you're not clear with the statement, so the table goes like this: first serial number, next load crossing the section or the point C. Okay, the load crossing the point C, then average load, okay, in AC here, and then I have average load in portion CB, that is here, okay, and final column is your remarks, right? So this is the pattern or this is the table that has to be put up, and how many such combinations can I get? Okay, so firstly, combinations, because there are 4 loads, I will get 4 combinations only. Each time I will put one load outside C and the other remaining towards the left side. So I will be distributing these 4 such that each time one load enters CB. First time one load enters CB, that is say 150 enters CB. So here in CB section, only one load is there, which is of 100. But in AC section, I have to take the average of 150, 80 and 120 with respect to the length. That time I will divide it by the length. Okay, so it is done like this. So first take the first load crossing is 100. So if 100 has crossed C, remaining are what? 120, 80 and 150, 120, 80 and 150, because 100 has crossed the section C. So here average load in AC, when I'm calculating these 3 loads, that is 150 plus, that is 150, 150 plus 80 plus 120 divided by their span 10. Okay, and average load in CB is now only 100, which is divided by its span. What is this value, please? 150 plus 80 plus 120 divided by 10.
35.
35. This is going to be 5. Which is higher? AC is higher than CB. So AC portions load is higher than CB. AC is higher than CB. Second combination is when this 120 also crosses. Okay, so load crossing C section is 120 kilonewton. So when 120 also crosses, so 120 crossed, and if 120 has crossed, matlab uska 100 is already there, and other 2 are remaining here, that is 80 and 150. So when 120 crosses, average load in AC is going to be how much? 150 plus 80 divided by the length, that is 10. And in average load in CB is going to be 100 plus 120 divided by 20. How much is this, please?
23.
23, and this is 11. 11. 12.
11.
11. Okay, again, AC portion is more than CB. Remarks. AC value is more than CB. Right. Third one. Third load. That is, what is the third load? 80 is crossing. So this is your beam. 80 also is crossed. Matlab 80 hai, 120 hai, and 100 is there. And here only one is remaining now, pap. That is 150. Correct. Now we will calculate. This is 80 crossing. let us calculate the load in portion AC. So in portion AC, what is the only remaining load is 150 divided by its length, that is 10. This is going to be 15. Okay, and coming to the other part, I have 100 and 120 and 80. So I'll have 100 plus 120 plus 80 divided by its span, that is 20. How much is this value?
15.
15.
Also 15. See, these both have become 15 now, and AC is equal to CD. And fourth one I need not do, but I know if 150 is crossing, यहाँ पे it will become 0, right? And यहाँ पे it will be all the loads, that is 100 plus 120 plus 80 plus 50 divided by 20.
22.5.
Right? So, but AC is less than CB. So this is our point, that is at when 80 crosses, where your AB and CB are going to be same, right? Now for this, you have to put this table, and after this, we will calculate the maximum bending moment. So while calculating the maximum bending moment, what we will be doing is we will be putting the regular ILD for bending moment. I say. Okay, with AB by L, but at this point it is equal, no? So I will have a distance C. Okay, I'll draw it both. This is your C, this is A, this is B. At point when this is crossing, it is same. So I'll place this 80 here. Clear? And then I have 120 and 100. And to the this side only one load is there, that is 150. So ILD, we know how it is going to be in this pattern for us beam, right? And this is 10 and this is remaining is 20. So AB by L is going to be 10 into 20 divided by 30. How much is this value, please? This is 10. This is 20.
6.66.
6.66. AB by L. This ordinate is 6.66. Get the ordinates for this and these two. Okay. So I'll call this as Z1, Z2 and Z3. We need to calculate the three ordinates. This I know, 6.66. Once we get the ordinates, then the load into the ordinate is going to give us the bending moment. It is going to be positive. So let us calculate the ordinates first. So in calculation of ordinates, 6.66 divided by 10 is equal to Z1 divided by this. Now how much is this? This is 2 meters. Matlab remaining distance is how much? 8 meters. Here this is 2, this is 2, this is going to be 16. Correct? So here 6.66 divided by 10 is going to be equal to Z1 divided by 8. Therefore, what is Z1? 8 into 6.66 divided by 10. How much is Z1, please?
5.3. Ma'am, 5.328.
32. Okay. Next, Z2. 6.66 divided by 20 is equal to Z2 divided by this. That is 16 plus 2 is 18. Okay. So 6.66 divided by 20. I shifted to this side of the triangle. B is 20 here. Okay. Is going to be equal to Z2 divided by 18. So get me the value of Z2. Similarly, 6.66 divided by 20 is going to be equal to Z3 divided by 16. Get me the value of Z3.
Ma'am, Z2 is equal to 5.99.
5.99. Okay. And Z3?
5.32.
5.32. Okay. So we are getting the various ordinates on the bending moment diagram. Right? These ordinates multiply with their loads over here. This table was put up to see at what load it is equal. So at 80 it is equal. So keeping 80 on point C, we drew the AB by L diagram and the ordinates and found the ordinates. So I'll write here only because you can see this values. So if I want to calculate the bending moment now, value is going to be equal to load. From here we'll take, okay, 150 into Z1, 150 into Z1 plus 80 into, this is known to us, that is 6.66 plus 120, visible hai, 120 into Z2 ordinate plus 100 into Z3. Correct? Substitute. 150 into Z1 is 5.32. 80 into 6.66. 120 into 5.99. And 100 into Z3 is 5.32. Calculate and tell me the value, please.
2582.8.
2582.8 kilonewton meter. Okay, 2582.8 kilonewton meter. Any doubts with this? Any doubts? So quickly we'll just, before going to absolute bending moment, because absolute bending moment has got a little, again, different procedure. So before going to the absolute bending moment, let's just brief out what all we did. We found the reactions RA and RB. To find the reactions RA and RB, you placed for RA, you placed the 4 loads like this. For RB, you placed the 4 loads in this pattern. Correct? And you know the ILD for RA and the ILD for RB. You used the load into the ordinates and got the RA and RB. After the reactions, we were calculating the shear force. For shear force diagram, these were your points C. So the first load was placed here, right, to calculate the negative shear force on point C. And then to calculate the positive shear force, we placed the last load on C, and this was the pattern. Okay. Here we get the positive shear force. Then when we were doing the bending moment diagram, we put up a table and we checked at what load your AC is going to be equal to BC. Correct? Once that was fixed, then we put up that load exactly at the point C with the other loads, and then we put up a regular AB by L influence line diagram and multiply by the load and the ordinates. Correct? Any doubt till here? Any doubts? Because this question has been asked every time. Continuous concentrated loads has been asked the other day when we checked, right? This is always asked. Now to find the absolute bending moment. Okay, to find absolute bending moment, there is a procedure. First step is find the resultant of the loads. Find the resultant of the loads. How I get the resultant? Now, what is a resultant? Resultant means if there are 4 forces, okay, and they have some value, I will find one force R, whose name is resultant, which will have the same effect of these 4 forces. Now, 4 different people pulling a table, and whatever is the total force applied by all of them, if I get one single force as good as same, it would be the resultant R. Okay, that concept. If I want to calculate the resultant, that means I have to take the sum of all the forces. How many forces we have? We have 150, 80, 120, and 100. How much is this? 450. Am I correct?
Yes, ma'am.
Yes, ma'am.
Resultant is 450. So first find the resultant of the forces. Okay, first step in absolute bending moment. The second step, once you find, no, not second step, once you find the resultant, you'll remember Varignon's theorem. All PUC students will know this. Varignon's theorem. Where did we use Varignon's theorem in mechanics? Whether it was concurrent forces or non-concurrent forces. You all were promoted for mechanics, right? Okay, sorry. I should be asking this question. Concurrent forces are something like this. They are passing through a single point. Okay, so their resultant also will be passing through that single point only. I have said F1, F2, F3, F4. These are called as set of concurrent forces. Matlab they are passing through one single point. So they are called as concurrent forces. And when I find the resultant of these four, that resultant also will be passing through the same point. Okay, so this is concurrent. Then comes the non-concurrent. Definition of concurrent is if they're passing through the same point. Non-concurrent would be they're not passing through the same point. So if I have random forces like this, anywhere, okay, they're not passing through a single point. These are non-concurrent forces. So when I find the resultant of this, correct, it is not passed. There is no one definite point. So once I get the resultant, I need to get its position, at what distance it is. That is where we find x and y intercepts, something called as x and y intercepts come. Okay, we have to find the positioning. To find this positioning, Varsha's theorem is used. What Varsha's theorem states is, you have n number of forces, right? You have F1, F2, F3, F4. Say F1, F2, F3 are three forces. You will take their moments about one point. So F1 into D1, F2 into D2, F3 into D3, say. Okay, so you are taking their moments about one known point. It will be equal to the moment of the resultant about the same point. So if I have forces like this, F1, F2, F3, say F1, F2, and F3. I'll fix a point here, O. I will get the perpendiculars of all these. So F1 is at D1, F2 is at D2, F3 is at D3. Okay, so F1 into D1 plus F2 into D2 plus F3 into D3 is what? The moment of the forces. This is going to be equal to, I will find a resultant of this all. Okay, so resultant is going to act here only somewhere, and it also will be at some distance d from that point where you took the moment. So r into d, that is, this will be equal to the moment of the resultant about same point O. This is Varsha's theorem. Okay, mechanics. It is coming from mechanics. I have to apply that Varsha's theorem here now to get the distance of the load. Now, what distance I am talking of, I'll tell you. So you have the four forces. What time is your next class? What time is your next class? Hello, all of you.
12:30.
12:30. Okay. I'll just find this distance and we will stop this numerical here. Tomorrow I have a class afternoon. I'll again continue this. So we have the four forces. This is 100, 2 meters each. So 100, and this is 120, and this is 80, and this is 150. These are concurrent or non-concurrent? Quick. These forces are concurrent or non-concurrent?
Non-concurrent.
Non-concurrent. They are not passing through a single point, right? So this is 2, 2, and 2. Now, we found the resultant of all these three. We don't know where it is acting. Okay, we found the resultant is 450. So say it is acting somewhere here. Resultant matlab it is going to balance. So it is acting somewhere here. All are down, so resultant also is going to be down. I want to know this distance. Now, how to get that distance? So what we will do, we will take the moment. We call this as x bar. Now, according to Varsha's theorem, the moment of all these forces about any point should be equal to the moment of this resultant to the same point. So let us say we will take this moment of all the forces at point O. Okay, taking moment about point O. So when I'm taking moment, 150 x bar will be or resultant into x bar, that is r into x bar, moment of the resultant is going to be equal to the moment of the forces. So that is 150 into 0 because it is acting on the point, plus 80 into this distance, that is 2, plus 120 into 4, plus 100 into 6. Correct, no? So from here, I know the value of resultant. Kitna hai? 450. So what is x bar going to be? This is the 0. 80 into 2 plus 120 into 4 plus, it's visible, 100 into 6 divided by, this 450 goes at the bottom. 450. Get me the value of x bar, please. Yeah, get me the value of x bar. We'll stop it here.
2.755.
0.75.
2.75 meters. Okay, so your x bar is 2.75 meters. Matlab it has crossed this load. So what we drew the figure was correct. 2 is here, 2.75 matlab yahan pe. So this distance is 0.75. Remaining would be 2 minus 0.75, 1.25. Right, and these are again 2. So the resultant of these forces is acting at this point. When we are finding the absolute bending moment, no? So this resultant should be placed at that central point. You should place the system such that I will get the absolute maximum bending moment. So for now, this much is sufficient, I think. All of you enter your USNs in the chat box. And tomorrow afternoon, I'm going to continue this class. The same numerical. Enter your USNs in the chat box and you can quit the meeting.